Welcome back, focused learners. Today, we're taking abstract mathematical concepts, the stuff that usually feels like just a bunch of numbers on a dusty chalkboard, and transforming them into something incredibly practical. We're building a powerful quantitative toolkit for real-world decision-making. If you've ever felt intimidated by advanced math, well, today's the day we flip that perspective completely. We're going to see how these tools directly apply to the world around us. But before we get into the weeds, I want to ask you a question. How do we actually predict the unpredictable? Think about the sheer chaos of the systems running our daily lives. Shifting global weather patterns, wild daily fluctuations in the stock market, or even the sudden spread of a global virus. At first glance, it just looks like noise, right? It looks totally random. But is it? How do experts look at all that chaos and actually figure out where it's heading? Well, the answer really lies in the language we use to decode that chaos. As our source material beautifully points out, mathematics applies to all aspects of the world, whether it is physical sciences, life sciences, or even finance and economics. So we really need to reframe how we view math. It's definitely not a hurdle to jump over. It's the fundamental language required to decode our reality. Think of it like the ultimate decoder ring for the universe. Okay, let's dive into this. Here's our roadmap for the explainer. We'll start with decoding our complex world, then move into probability and statistics, the language of functions, modeling real-world phenomena, and finally, making informed decisions. Let's get to it. Section 1. Decoding our complex world. Measuring the present. Because before we can predict the future, we have to know exactly what's happening right now. Moving on to Section 2. Probability and statistics. Foundations of prediction. This is the first major tool in our kit. So, any massive dataset can basically be broken down to answer two main questions. First up, we look for measures of central tendency. Basically, where is the center or the most typical value of our data? But, just knowing the center isn't really enough. We also absolutely need measures of dispersion. How widely spread out is that data around the center? Is it all tightly clustered and predictable, or is it completely wild and scattered all over the place? Now, what's really interesting here is the juxtaposition between what math expects and what reality actually delivers. Think about theoretical frequency. This is the expected mathematical probability. If you flip a coin, theory says you're going to get heads exactly 50% of the time. But then we have relative frequency, which is the observed outcome in practice. If you flip that same coin 10 times, you might end up with 7 heads. Probability theory is really all about navigating that exact tension between perfect mathematical theory and messy real-world observation. And obviously, this isn't just about coin flips. Probability theory leaps right out of the abstract and into the real world. We use Venn diagrams to visually map out complex, overlapping relationships between different events. Meteorologists use these exact models too. In fact, a 30% chance of rain actually means there is a 100% chance of rain for 30% of the forecasted area. Kind of mind-blowing, right? And over in the corporate world, analysts use probability for risk assessment, evaluating the likelihood of threats so they can make high-stakes business decisions. Section 3. The language of functions. Dynamic relationships. Let's zoom in on what is literally the absolute backbone of higher mathematics. This is where things get really fun. Functions take us from static, stationary data points to dynamic, moving relationships. Simply put, a function models the relationship between changing quantities. It essentially tells us the story of cause and effect. It answers that crucial question. If I change this one specific thing over here, exactly how much will it change that other thing over there? Comparing these function types side by side really reveals how we model different behaviors. Think of this as your cheat sheet. A linear function creates a sloping line, which is perfect for tracking steady stock market trends. Then you have a quadratic function, which forms a U-shaped parabola. That's the exact mathematical curve an architect uses to design a structurally sound bridge. Hyperbolic functions give us two curves with asymptotes, those invisible lines the curve approaches but never quite touches, mapping out complex inverse relationships. And then, of course, we have the exponential function. That's the rapidly growing curve epidemiologists use to model how fast a disease can spread. Now, I want you to do a quick mental simulation with me. Imagine you have a digital slider for specific parameters, like A, B, M, C, and Q. If you physically manipulate the M parameter, the slope of a line tilts. If you tweak A, a parabola might stretch out or even flip upside down. By simply sliding these interactive parameters around in an equation, we instantly warp the shape and position of our visual curves. That is the incredible power of algebra translating directly into geometry. So the crucial point is that by understanding these 5 unique graph characteristics, the domain, the range, where the intercepts cross the axes, where the turning points peak and dip, and those boundary-defining asymptotes, we unlock a completely new language. We gain the ability to describe highly complex behavior using words, equations, and visual representations all at the exact same time. Section 4. Modeling real-world phenomena, solving massive problems. Let's zoom back out to see how professionals actually wield these specific graph features. The applications for this are literally everywhere, and they are absolutely critical. When a new virus emerges, epidemiologists don't just guess. They immediately apply exponential functions to model the disease's spread and advise on public health measures. When financial analysts look at years of messy market data, they use linear regression to cut straight through the noise and predict future stock trends. And when architects spend massive rivers, they rely on the absolute mathematical certainty of parabolic curves to ensure those bridges hold the weight and don't collapse into the water. Which brings us to our final section, Section 5, Making Informed Decisions, Actionable Intelligence. This is where we tie the entire quantitative toolkit together. And this brilliantly illustrates the real-world workflow. It moves chronologically, starting with Step 1, gathering your descriptive statistics, so you can understand what is happening right now. Step 2, choosing the correct function model, whether that's linear, quadratic, or exponential, to map out the relationship of your variables. And finally, Step 3, using that model to project into the future and make a highly informed prediction. Let's bring this directly back to you, and more importantly, your wallet. Think about financial mathematics. When you invest your money, you're relying on compound interest to maximize your growth over time. But here's the thing, that compound interest isn't linear. It is an exponential function. Understanding how that exponential curve works and how time is the parameter that accelerates your growth is the exact key to leveraging math for your own personal financial success. So, as we wrap up this explainer, I want to leave you with a provocative thought. We've seen how these tools decode the weather, build bridges, and grow investments. The math isn't just theoretical, it's highly actionable. So how will you apply these quantitative proficiencies to your own life choices? Think about the data you interact with every single day. You now have the toolkit to look at the world just a little bit differently, to see the relationships hiding behind the numbers, and to start predicting the unpredictable in your own life. Keep exploring, stay focused, and go use these tools to decode your world.